if we look at this function, it looks like the only changes that we're making to a basic cotangent are in the input. So we're only doing horizontal transformations. I think those are the more interesting ones visually when you've got tangent and cotangent. A vertical flip is kind of interesting because it changes something that's going up to something that's going down and vice versa. Stretches and translations or shifts aren't, I don't think, all that visually interesting, because basically you've got something that's kind of steep going up or something that's kind of steep going down, and stretching it and moving it, it doesn't look all that different. Okay, that's not to say that vertical transformations aren't significant. The difference between 1 and 2 can be a big deal. Okay, but visually it's much more striking to see, I think, the horizontal changes. Okay, so I want to remember that with cotangent my period is pi. So cotangent is going to do its thing once over any interval of length pi. You want to start and end with an asymptote. The asymptotes for cotangent are at multiples of pi. So that's actually pretty nice, because I can just say I want my input to be between 0 and pi, and that will correspond to 1 period. With tangent, in order to start at an asymptote, we adjusted to negative pi over 2 and positive pi over 2. All right, so I'm going to put my input. Oh, you know what? Let's rewrite this in factored form. This is cotangent of 2 times x plus pi over 6, if I factor out that 2. Again, not absolutely necessary to do this, but that way I can do a visual check at the end. Have I actually shifted things left pi over 6? Okay, so 2 times x plus pi over 6. So to solve for x, we'll divide through by 2. So we get 0 less than x plus pi over 6 less than pi over 2. And let's subtract our pi over 6. Okay, so I get negative pi over 6 less than x less than, let's see, I want to do pi over 2. Let's get a common denominator by multiplying by 1 in the form of 3/3. So that's 3 pi over 6, and then from that I'm subtracting pi over 6. That's going to give me 2 pi over 6, which reduces to pi over 3. Okay, might be useful to have that in non-reduced form as well, although I'll certainly label it in reduced form. Okay, so what's the period? Well, there are two ways that I can get that. I can say it's going to be the original period pi divided by this number that we're multiplying by, which is 2. Okay, and it's positive, so I don't need to worry about an absolute value. If it was negative, talk about that in a moment. Okay, but then I just have the absolute value. I should also be able to get that by saying that's ending point minus starting point. So 2 pi over 6 minus a negative pi over 6, that's 3 pi over 6. That does reduce to pi over 2. Excellent. So that's my period. That means that the increment is going to be 1/4 of that, which would be pi over 8. Okay. So my x values, oh my goodness, I'm going to start at negative pi over 6, and I'm going to count over by pi over 8. Think I'm going to want to get a common denominator here. The smallest common denominator is going to be 24. Okay. So if I multiply pi over 8 by 3/3, that's going to give me 3 pi over 24. Negative pi over 6 is the same as negative 4 pi over 24. Okay. So if I add 3 pi over 24 to that, I'll get negative pi over 24. Add 3 more pi over 24, I'll have 2 pi over 24, but that can reduce to pi over 12. Add another 3 pi over 24 to that, I'm going to have 5 pi over 24, which doesn't reduce. And another 3 pi over 24 will take me to 8 pi over 24, which does reduce to pi over 3, which is supposed to be my ending point. Okay, excellent. So they're a little messy, but we can handle it. Okay. So let's see, we're starting at negative pi over 6, and I think I'm going to actually want to mark off pi over 24th as my tick marks here. So each tick mark is a pi over 24. Whoops. Let's make them evenly spaced, shall we? Okay, so I'm starting at negative pi over 6, which is negative 4 pi over 24, and that's going to be the location of an asymptote. My next important point was at negative pi over 24, so let me just label that. Then 2 pi over 24, which was pi over 12, I'll label that. Then 3 more to the right is 5 pi over 24, and then 8 pi over 24, which we said reduced to pi over 3, and that's going to be the location of my ending asymptote. Okay, now we didn't do any vertical transformations, so the y values that we care about are 1, 0, and negative 1, and cotangent is the one that's always going down. So if we start up high at a quarter of the way through, so at negative pi over 4, we'll be at a y value of 1. Halfway through, which is at pi over 12 in this case, we'll be at 0. 3/4 of the way through, at 5 pi over 24, we'll be at negative 1. And so then I can connect the dots with this beautiful and lovely curve. Okay. That would be 1 period, and then we were asked to draw 2. So if this distance was the distance between asymptotes, that was the length of 1 period. My next one would be over here. And I'm just sort of sketching that roughly freehand. If I want to, I should maybe find the location of this asymptote. So that would be at pi over 3, plus we want to add 1 period to that. So plus pi over 2. Looks like I want a common denominator. So this would be 2 pi over 6 plus 3 pi over 6. That's going to be at 5 pi over 6. Okay. Excellent. So that gives us our graph of cotangent. I said I wanted to discuss what happens if we have a negative multiple of x. We're going to see more of this in the next chapter when we start looking at identities. But if I look at the unit circle definitions of things, so here's my angle, which I'll call little x, and then it intersects the unit circle at a point capital X, capital Y. Okay. If we look at our definitions of things, sine of x is the capital Y value, and cosine of x is the capital X value. So when I look at tangent of x, that was the ratio capital Y over capital X. That basically means it's sine x over cosine of x. Okay. And if I look at cotangent of x, that was capital X over capital Y. That basically means it's cosine of x over sine of x. Okay. So I've got this relationship between those functions. That's going to allow me to figure out whether tangent and cotangent are even or odd functions. So let's say I wanted to look at tangent. I'm going to plug in the opposite input. So I'm going to plug in the opposite of x. I know if I get the same output, if I just get tangent of x, then tangent is even. If I get the opposite output, if I get negative tangent of x, then tangent is odd. But I'm going to use the fact that tangent is sine over cosine. So if I'm plugging in the opposite of x to tangent, that's equivalent to plugging it into sine and cosine and forming this fraction. But now I know that sine is odd, so this would be the opposite of sine of x. Cosine is even, so my denominator is just cosine of x. Well, that introduced one negative sign, so that gives me negative. I can put that negative sign in front if I want. Sine x over cosine x. That's negative tangent of x. So tangent is odd. And the same argument's gonna apply to cotangent. I'll leave it as an exercise for you, but if you plug in the opposite input to cotangent, you should also get out the opposite output. So cotangent is also odd. So for both tangent and cotangent, opposite input gives you opposite output. That does show up in one of the homework problems, so I wanted to make sure that I mentioned that.